Okay, good morning and good afternoon to those joining us in Europe. I would like to introduce Doug Wicks, who's here from the DOE. He's a program manager, director, apologies, working with ARPA-E, and he's going to speak to us for an hour about geologic hydrogen. And then we're going to break into a smaller group in 202, okay? But we'll let Doug set the scene. And if you have any questions online, please raise your hand or write them in the chat box and we'll get to them at an appropriate point. We are going to record this presentation and the recording has started, so if you don't want to be part of that, then you know what to do, and we will post it after the meeting. And with that, I'll hand over to Doug.
Okay, thank you. Okay, so kind of quickly, we have three of us that I know of involved, might be a fourth, and with me is Sam Falzone. Sam is a contractor who works with ARPA-E, and he actually understands geophysics. And then also online we have Otan Montero. Otan is our tech to market advisor for the projects I lead. He also has a background in the oil and gas industry, having worked for Baker and Hughes, and has a degree in geology. I myself am an organic chemist. Here talking to you about stuff, so keep that in mind. If you ask really hard geologic questions, I'm going to punt to that. So what I'm going to talk to you today about is geologic hydrogen, and this is a topic I've been sucked into about almost 2 years ago now, and really getting more and more excited about the potential for this. And quite luckily, just last week, Science published a really nice article on geologic hydrogen, focusing a lot on the work that we've done the background work we've done at DOE. So my colleague Emily Yednek is quoted quite a lot in this, but more importantly, the work from USGS. Jeff Ellis out of the Denver office is fully dedicated to this activities, and I will be giving an introduction to you guys to have him give a seminar. He has some amazing, amazing results, which I'll touch upon. Wrong button. First off, there is no funding opportunity. This is the first thing we have to say. When we talk about these things, there's no guarantee of a funding opportunity coming out. But one could say I wouldn't be out talking to you unless I thought there was a possibility. And really what I'm here today is to gather information. And really, I'm asking for very direct input from the team here at Schlumberger to look at technical possibilities, potential metrics, and is this viable? Is it the overall opportunity? So if you're doubting what I'm saying, please tell me. If you think I'm on the right track, please tell me. If you have suggestions on the way a potential program should be structured, tell us. It's really quite important for this because it is a totally new area we're looking at. So coming back to why are we interested in hydrogen? You actually have some colleagues today in Washington, D.C., talking to the DOE. The executives are in there for the big presentations. And they'll be getting a whole section on hydrogen. Not geologic hydrogen, though. They'll get the official DOE version of it. But it's really looking at the future to say, between now and 2050, IEA conservatively, and I say conservatively, projects that we're going to need 520 million tons of hydrogen in 2050, with about 200 million tons they're forecasting coming from SMR with CCUS, and then the rest being based on electrical consumptions. And it's going across all types of things, shipping being a big one. All the major oceanic shippers are pivoting towards hydrogen-derived fuels, whether methanol or ammonia. it's going to really, they view the only way to really get the energy density they need is from hydrogen-derived fuels. Same thing with aviation, and these all require inexpensive hydrogen. So how is it done today? Pretty straightforward method. You take 2 kilograms of methane, you put it into a steam methane reformer. Simplistic view is you put it in natural gas plus steam, you do a shift conversion, and you get hydrogen out the other side. A very straightforward reaction practiced on huge scale from this with carbon dioxide. You get 1 kilogram of hydrogen from 2 kilograms of methane and 10 kilograms of greenhouse gases that you have to deal with. So it's actually one of the largest contributors to greenhouse gases right now, even at the low production we have. Rough costs are somewhere between $2 and $2.50 per kilogram of hydrogen for that. Primary use right now is fertilizer and in petroleum refining, basically for upgrading in the oil industry. So projected going forward, and there's lots of stuff. I mean, there's large amounts of money. The US government is dumping $4 billion, I believe, right now into hydrogen hubs. The vast majority of these are going to be going into carbon capture with SMR. And to make that 200 million tons that we're projecting in the future, it's 400 million tons of methane, roughly 20% of the global production of natural gas right now. They're talking about just going into the hydrogen side. This is going to produce the 200 million tons of hydrogen. We have 4 gigatons of CO2 directly coming out of this to sequester. So that's 4 billion tons of CO2. And this really doesn't count the CO2 and methane leaks across the line, which are going to cause a lot of other issues. Less than 60% energy efficiency. When you add it in, SMR is roughly 60% BTU conversion from methane into the hydrogen. This is less than 60% because you're spending a lot of energy capturing the CO2 and driving it underground. I've seen cost targets of $2.50 to $3 per kilogram for the hydrogen coming out of this. I've yet to see anybody who's demonstrated it yet at scale. The other thing to look at is green hydrogen. This is the other majority of what the IEA is projecting. Take 18 kilograms of water, 45 to 50 kilowatts of electricity, and you get a kilogram of hydrogen. There's 3 routes out there being pursued: alkaline solid oxide electrolyzers, polymer electrolyte, PEM cells are being looked at for this. Your energy efficiency, so energy in versus hydrogen energy out, is somewhere in the 60 to 68% range before compression. So please keep that in mind. The numbers I'm talking here are the hydrogen bubbling out of the electrolyzers. To do our 320 million tons of hydrogen, and again, this is a conservative number. I've seen projections where people are now talking about 1 billion tons of hydrogen needed. So keep in mind these numbers could be double it. You have to put in 15,000 terawatts of electricity, terawatt hours, excuse me, to do this. And this is going to require somewhere between 2 and something over 5 terawatts of generation capacity to do this. So the higher number is based on intermittency. So everybody comes back, and you'll see this coming forward, such as the DOE Earth shots. To get the really cheap hydrogen, they say we're going to have solar and wind. It's going to be almost free. But then you have to worry about capacity factors. The sun only shines, wind is only so dependent. And if you have to start shipping in electricity from 2,000 miles away, the costs go up. So the higher number is for intermittent. And keep in mind the global energy generation capacity right now, everything, nuclear, fossil fuels, wind, everything is 8 terawatts of capacity that we have in place right now. So this is a huge amount of electricity just to do a small portion of our energy demand. The targets, current costs are somewhere well over $3 per kilogram without a subsidy. There is in the US a $3 per kilogram subsidy, but still it's not free, even with $3 subsidies. The DOE, what you guys your executives are hearing today is they're going to come back and say, we're going to do $1 per kilogram. And they assume electricity much lower than 20 cents, or much lower than 2 cents per kilowatt or $20 per megawatt. That's basically a solar panel sitting next to the electrolyzer. Okay, the sun don't shine all the time. And they have in their imagination a 75% efficiency of energy and a 75% availability of intermittent electricity, which is pretty hard to do. So keep that in mind. So green hydrogen also has a materials challenge, and this is really my way into it, was from the mining side, because I have programs in the mining space, to look at what's required for this. And for 320 million tons of electrolyzer capacity, I took some of the numbers off of here, but for intermittent, we're going to need 2 to 4 times that electrolyzer capacity, just waiting for the intermittent electricity to come along. So we're going to be looking at somewhere around a billion tons of electrolyzer capacity if we want to use intermittent. PEMs, platinum group elements, big challenge on how we're going to get that. I've seen forecasts that are, anywhere up to 50 times current production of iridium is going to be required for PEM electrolyzers. Solid oxide systems, you have lanthanum and yttrium as the primary solid oxides. And even alkaline, you're looking at nickel and zirconia that we really don't have a lot of. I mean, there's a fair amount of nickel, but class 1 nickel for this, you're competing with batteries. And what everybody forgets about is what goes into that intermittent electrical generation. So for 5 terawatts of wind and solar, it's about 50 million tons of critical materials go into that, to generate that material. So huge numbers. By the way, 50 million tons is 10 times our current production of those materials, just to power hydrogen. So you're going to hear people talk about pink hydrogen. There's going to be a presentation to the Schlumberger people today saying, oh, nuclear is going to take care of it all. If we do that and we look at small modular reactors as being pushed by the DOE right now, these are about 30 megawatts per reactor, 0.27 terawatts per year per reactor of total terawatt hours. You need about 56,000 of these by 2050 to do that. And by the way, the base electricity price, the lowest I've seen is $50 per megawatt or 5 cents per kilowatt. You take that into the hydrogen costs, and just your electricity cost is about $3, $2.50 to $3, just for the electricity. So pink hydrogen, by the way, I hate colors. I'm totally convinced that somebody's going to look at this and say, with all these rainbow colors, and they're going to say, woke hydrogen, we don't want it. Get ready for it. So what lies beneath our feet? I kind of look at it and say, what can we do? And this is why I'm here, because you guys think about what's under our feet, and how do we exploit it, and how do we get through it. So, oops. So the Earth is continually producing hydrogen. I mean, there's a huge amount of hydrogen being produced by the Earth. Several different methods: radiolysis in the deep earth, mineral oxidation, microbial effects, thermal effects, all types of things taking place in the deep earth. The numbers I've seen are somewhere in the billions of tons of hydrogen that's being generated every year by the Earth. We just don't pay attention to it. A small amount of it does come up to the surface, and we'll talk about that. Roughly 30 million tons is now the accepted number. It's probably going to rise up pretty soon once they fully characterize what's coming out of Yellowstone and other thermal springs. That's currently coming up, and it's diffusing out. Some of it's escaping into space. Others of it is reacting with things in the air. So, seeps are found worldwide. So these are locations where people have actually found hydrogen percolating to the surface. And when we look at this, you come back and this is either gas coming out, free gas percolating out, inclusion gas where they're finding it in rocks, or water saturated with hydrogen. So they're finding it. You'll see a huge emphasis on Russia and Western and Eastern Europe. For some reason, the Russians really like to track all the gases coming out of their systems in the U.S. and publish it. In the U.S., we don't pay as much attention to what's coming out in the gases, or we don't publish it. So lots of stuff. You'll see a number in the United States. By the way, this is filling in very rapidly since Slava wrote this paper. There's a whole bunch now being found in Brazil and Africa are coming up. And one of the things you see is, this is one of my favorite ones. This is the eternal flame in Turkey. This is where the Olympic torch came from. It's a high hydrogen seep that's been burning for at least 4,000 years. It's been going there, and it's got a high concentration of hydrogen. It's got some natural gas in it, that's why you can see it. There are other hydrogen seeps that are burning that you can't see because hydrogen burns clear. And so they've found some basically by running into, basically getting burned as they got close to it. The other thing hydrogen does when it percolates to the surface, as shown on the right, it causes what's called a Ferry circle. And these Ferry circles are found all over the world. And the hydrogen comes up and really interferes with plant metabolism, so you get very limited growth taking place in these. So the concentrations of gas coming out in these locations can be really high. And this is a graph looking out, and this came out from Alexei Milkov last year, publishing. He went through and took all of the reports of hydrogen, the concentrations, brought them back into rock types, and began to say, well, how much is there? And so on the left is the concentration of hydrogen. And what I want to really point out to everyone is these types here on the left. These are not the types of rocks you guys have been drilling in for oil. Okay, these are very different areas. And so somebody's always asked, well, we've poked enough holes in the ground with the oil companies. If there's hydrogen out there, they would have found it. No, I mean, first of all, they're not looking for it a lot of times. They don't measure it. And second, you're just drilling in the wrong places for this. But there's concentrations out there of all different types of range, all the way up to 98% has been found in deposits that are out there. We'll be touching on this. And so where does hydrogen accumulate? One of the classic examples is outside of Bamako in Mali. And this is looking at a system and looking at it from the space, looking down on it. This is a huge Ferry circle, right? You can see the distance, about 1 kilometer across. A group out of France, I can't remember which one of the energy companies of France is trying to exploit this. By the way, they found this by accident. They were drilling for water, and somebody walked up with a cigarette and the well blew up. You know, and it was just like, what? You know, this clean explosion just blew everything up. And, you know, somebody heard about this in France and said, natural gas. And they went down and blew up a few more things, but came back and really started doing measurements saying, oh, hydrogen. And the graph on the right is the emissions across this fairy circle. So they're picking up hydrogen that's diffusing out of the ground into the air. And when they drilled into it, they found out it was 98% hydrogen, free hydrogen gas. And this is a area where they've looked at it and they've drilled down through this and actually found hydrogen at a whole bunch of different levels that's being trapped across the systems underneath a variety of sedimentary traps, competent traps that hold it in place. And they're still working on how big this is and can they commercially deploy it. The problem is outside of Bamako is not a very politically stable area. And the other question is, I mean, the other thing I do know from talking to these people is they don't think it's enough for a hydrogen pipeline. And so how are you going to get this hydrogen from the middle of the desert in Mali to anybody who wants to pay for it? Right now, there is a small generator running off of this that powers the little town where this is located. But it tells us that you can get concentrations. Other concentrations have been found around the world that rival this, particularly in Australia. Okay, and the question came back, one of the first things we did and said, could you make money off of this? And at $1 a kilogram. And this is a calculation we did early on and said, well, you know, if we've got 1,000 or 100, only have to drill 100 feet. And, you know, you could use water drilling rigs, use PVC pipes going down, cheap costs, and the hydrogen flux at 1,000 cubic meters per day, which is about what these guys have published. Again, it's not a huge amount, you know, saying that really this could come up with, at this depth, $1 per kilogram. Of course, then what are you going to do if you only have 1,000 cubic meters per day? It's really not worth looking at. And we have to look at that, you know, this is a small fraction of what an average natural gas well is. So the question is, can we take this and stimulate it? So it has enough to power a little PEM electrolyzer for that, and probably continue to power, you know, part of Bamako, Mali with this. So, you know, and a number of things are going to come back, and we have to look at concentration. And again, this is for natural deposits. You know, we have to look at concentrations, how deep they're found. And you can see conventional reservoirs over here. This is your guys drilling for oil. We're finding low concentrations, and there's actually really good reasons why there's low concentrations in natural gas, because if it was there, it could be turned into something else. But we can find, you know, a variety of different concentrations. The thing I want you to pay attention to, again, is the hard rocks, is where you're finding high concentrations close to the surface. All the high concentrations are in hard rocks. So it's taking us away from where the oil and gas people like to drill. So where am I going with this? So we have some isolated wells that are going to give us 1,000 cubic meters per day, potentially around the United States. And so the question really comes back to say, what are we going to do? By the way, this is the most recent site that was found in Brazil. Somebody's been flying over Brazil looking for these funny circles, and that's a hydrogen seep. So this is from the science article that just came out, and begin to look at and try to understand where this hydrogen is coming from, and then why. Take that information and come back to say, why am I here talking to Schlumberger about this? So there's a variety of mechanisms. As I said before, you have the radioactive methods, you have the iron oxidation, you have abiotic methods and the likes, with a whole bunch of stuff eating it and surviving on it. By the way, the vast majority of the hydrogen that's produced on the Earth goes into microbes. Keep in mind that underneath our feet is well over half the biomass on Earth, and the majority of it is powered by hydrogen. So what's happening underneath our feet? Again, we have radialis, serpentinization, deep-seated, which is, I don't know, tectonic plates ramming together and causing all types of piezoelectric reactions to take place in hydrolyzed water or powered water. And the loss mechanisms, we have some coming to the surface, small amount, microbes and abiotic reactions. And the abiotic, you guys can look at and say that's future oil. So this is where a lot of the oil is coming from. And what I'm going to posit to you guys is we can avoid these. These two can be avoided, the abiotic reactions. And if I look at the generation of the system, I can control the chemistry of serpentinization. So this is a chemical reaction. Radialis is deep on the Earth, unless we're going to, find a way to inject thorium down into the deep Earth and allow it to power the formation of it. The serpentinization I am very attracted to, because this is, as a chemist, again, I'm a chemist, I look at this and say, I can drive this reaction. And this is a specific reaction we're going to look at. Very simple, iron 2 compounds plus water gives you iron 3 oxides, rust, and hydrogen. It's a very straightforward reaction. The important thing to keep in mind, if you look at the Earth's crust, 5% of the Earth's crust is iron 2. So if you look under the feet, wherever you are, you're going to find iron 2 beneath you. So 5% of the total Earth. Everything below the surface, again, is very reduced. We live in the oxidized portion of the Earth. The reduced portion of the Earth is beneath our feet, waiting to be oxidized. The one thing I should have written on this, and I need to update this is an equilibrium. This reaction is an equilibrium reaction. It's not a one-way. It's not thermodynamically precluded, but it is not favored based on equilibrium. Equilibrium lays way to the top. But if you take out the hydrogen, it is a very fast reaction. So you can get this reaction to go in what I like to say is the attention span of a graduate student if you pull away the hydrogen. So in the deep Earth, quite luckily for us, in the deep Earth, equilibrium lays to the top. If the equilibrium did not weigh to the top in the deep Earth, we'd be living in a hydrogen atmosphere with no oxygen or water, because there's enough iron 2 down there to consume everything. So 5%. So what is the potential? If you look at this in this primary target, in situ oxidation of iron 2 to water, 5% of the Earth's crust being iron 2. Estimates on this, looking just not at the non-ocean side of it, so just on land, within the range that you guys can get to, are 10 to the 15th tons of hydrogen potential is laying beneath our feet. I mean, that's millions of billions of tons for those who could do the conversion quick in their heads. So it's millions of billions of tons. The thermal energy of that millions of billions of tons far exceeds all the fossil fuels underneath our feet. It's just sitting there. I talked about Jeff Ellis and at USGS. He's doing a fantastic job of modeling right now resources for this. So he's going through, and I fully encourage, if you haven't had any contact with him, that you guys have him in, give a seminar, which will be much more informative than mine. in terms of the basic science of it. But he's going through developing models where they're looking at sources, migration pathways, reservoirs, traps, seals, preservation, timing, taking all the things that have been done before for oil and gas accumulations by the USGS. So really in-depth models of this stuff. Really looking at the important differences. Hydrogen generation is really fast. It's not like oil and gas, not like methane, which, you're looking at geologic time spans to get your future oil. This stuff is forming fast. Again, if you allow the hydrogen to diffuse away, the reaction's almost instantaneous. Hydrogen's much more diffusive, it's slippery, it's going to diffuse away, and this has big impacts on this. There's good solubility differences. At ambient pressures, the solubility of hydrogen water is close to nil versus methane. And it's also more reactive from both biotic and abiotic systems in the hydrocarbons. So there's a bunch of challenges we have to look at. And he takes these kind of systems and has developed some great mapping capabilities. By the way, can one hydrogen system up? He's coming back saying, can I come up with one system to model all this? And, the question's going to be no. But quite interestingly, if you begin to go through, again, he already has the programs being set up. You can go through and type in the different variables that you want to have and begin to map where should we be looking for hydrogen. And this is the first of his maps. And it was really great when he came up with this map, because I looked at him and I said, I told you so. This is exactly where I told him we were going to find hydrogen. Most importantly is this big thing in the middle. This thing right here. That's the mid-continent rift. That's a several billion-year-old geologic formation where the Earth had been pulsing up huge amounts of magma. The whole thing across from Oklahoma all the way up to Michigan, back down or up to Canada and back down to Michigan. It's loaded with olivine. Same thing is found off in the Carolinas, and there's a belt going across Arkansas. These are massive deposits. One thing I want you to keep in mind is that oxidation of hydrogen, of iron 2 to iron oxides, forms a 60-40 mixture of magnetite and hematite. Don't ask me why, I just can write it out. Find yourself a good geophysicist or geochemist to explain why. But the important reason I say that, right there, that's the iron range of the United States. It's all magnetite. The taconite that's up there is 60% magnetite, 40% hematite. I wonder where it came from. It's one of those things that you look at, and I've seen calculations, done back of the envelope calculations with some of the guys up at the University of Minnesota Duluth that talk about hundreds of billions of tons of hydrogen came out of the Iron Range in the past. So you might be breathing hydrogen. The water that you have inside of you might come from hydrogen from geologic sources. So what I'm now we're going to get into kind of what I'm thinking about, and really what I want your inputs in. And, this is really quite critical for us. Again, when we talk about 10 to the 15 tons, as I've told people, this is like, the multi-billion-dollar lottery tickets. This is worth spending $20 on, just in case. Because it's potentially a limitless supply of energy for us. And so we're looking at 3 tracks. And so as I imagine this, we're going to talk about, can I affect the chemistry of this reaction? Can I stimulate it? Are there ways to catalyze this reaction? And there are, by the way. I can tell you that people are coming up with ways to catalyze this and make it go faster. We need work in the geology, really coming back identification of these deposits far beyond what the USGS is trying to do, because then we need to bring in things like permeability. How do we identify competent cap rocks? Because really what we want to do is be able to stimulate this and concentrate it under the ground. By the way, people have asked me, could you dig up these rocks and do it? And it's like, no. In an olivine rock of 10% FeO, you're looking at 0.5 kilogram per ton of rock, 0.5 kilogram of hydrogen per ton of rock that you dug up. So it's not worth digging up billions and billions of tons of this stuff. So, and then engineering. I kind of view this as really a massive engineering challenge. Drilling, how do we get down into these locations? How do we do gas separations for the processes? Just going to come back and do what's the concentration coming up? And how do you manage the reservoir as a key topic here? And I like to look at simplistic views and kind of, again, coming back from the oil and gas region, saying a simplistic view, can we just drill down and bypass all these parasitic reactions? Can we drill past all the future oil, all the peat deposits and the likes, which is future oil for hydrogen? Can we drill past the microbes that are making your future methane and get down there where the temperature is 200 degrees Celsius, there's nothing alive, and just suck out the hydrogen, shift that equilibrium from a very straightforward process? Can we take a simplistic view and really take lessons from our geothermal colleagues who are looking at enhanced geothermal? And this basically drill a couple wells, inject water into an appropriate ore, suck out the hydrogen. It's been oxidizing the iron, so you get no digging, no byproduct separations. By the way, the one thing I want to note here is this is not an energy carrier. This is a primary energy source. So unlike the electrolysis of hydrogen, it'd be pretty stupid to electrolyze hydrogen like you see Japanese are talking about doing, and then shipping it up to Japan, burning it to make electricity. It's kind of like you're losing a lot of efficiency in doing that. This is a primary source would be coming out. So not an energy carrier, just the primary source. And by the way, the EGS people are finding hydrogen. If you take a geothermal well in Iceland, it's producing 1 million kilos of hydrogen per year. So it's happening, and it's vented into the air, along with all the CO2 that comes up with the rocks. The EGS people, you talk with them, and I asked them, what about hydrogen in your systems? And they're like, oh yeah, we see it. We don't tell anybody about it. We find a lot of it when we start, and we find a lot of it when we stop. And if you think about this, they're not pumping a lot of water down when they're starting and stopping. So they're actually getting a continuously fairly high flow. I have talked to one geothermal company, and we were talking about hydrogen in the systems, and he's like, yeah, we find this stuff. And I was like, did you ever find high concentrations? And he was like, yeah, we did. We found that it was in the explosive range, and it didn't drop over time. And I asked them what they did, and they said, shut the well down and move down the street, because they did not want hydrogen. They were a geothermal company. And it's like, really? Silos, it's called. So can we do this? I mean, this is really just very straightforward engineering. I'm sure you guys are spending a lot of time looking at enhanced geothermal to say, how do we drill and frack and get all this to work? So it's been mentioned when we talk about stimulating this reaction. This is some really neat work, again, that was published last year. So everything, by the way, is, you'll notice a lot of 2022s coming here. So this is a building topic. This is a collaboration between the only two labs in the whole world up until 2022 that were looking at stimulating geologic hydrogen. And that's from Francois Osselin, and actually he didn't even make the list here. There should be another one up there. Eric O'Shea out of Bern. I'm not sure why he didn't get on this, but they're looking really, can we get hydrogen production and geologic storage of CO2 at the same time? And the gist of this work and subsequent work that's coming out of this, again in 2022, or now in 2023, is mineralization of CO2 greatly enhances the production of hydrogen out of these systems. They have not looked into a existing deposit to do this. This is all laboratory experiments so far, where they set up a fairly complex pressure cell and are able to go through and monitor this. And there's a number of groups that are now developing similar systems. So I think we're going to see laboratory experiments that will allow us to understand how do we catalyze this reaction going forward with that. So kind of as a background, the other thing I want to emphasize to everyone is this is key for us, and this is one of the things that we talk about the risks, is we don't want to avoid, or we want to avoid trading one problem for another. It doesn't take a lot to all of a sudden type in hydrogen, greenhouse gas, and you come back to Steve Hamburg's paper on the greenhouse gas impact of hydrogen, which is, even though hydrogen's not a primary greenhouse gas, it does react with radicals in the air, which is, if you think about the radicals in the air, that's the decomposition methods for CO2 and methane. So one of the big issues we're looking at is how do we make sure when we inject stuff in the ground that there's not hydrogen spewing out from around the edges. So kind of wrapping up here, look at this. And these are the questions I'm looking to have you guys answer. Is we have risks. I mean, there's a lot of risks here. I mean, how do we, avoid that inadvertent release to the atmosphere? So if we're stimulating over here and it starts bubbling up on somebody's spring next door, how do we avoid that? So again, how do we maintain competence of that? Can non-leaky reservoirs be developed? So can we develop these things where we have it in a position that the hydrogen accumulates and we can then pull it out from the system? And again, will increasing rock permeability lead to production increases? The production increases we need, to get the water in there and pull materials out. How do we look at permeability for that? And can we get stimulation methods? Can we do this stuff like CO2 mineralization, or can we put in magnetic nanoparticles? Can we put in electrical stimulation? Can we do any of a variety of things to stimulate this to increase the production by orders of magnitude to make this viable? Again, so we need to get that flux up. 1,000 cubic meters per day per well is not going to pay for a well. What's going to be the seismic impact of this? We're doing a whole bunch of stuff underground. This is the first question everybody asked me. It's just like looking at it, you're injecting something into the water or into the underground. You're going to have earthquakes. You're going to cause all these problems. Just like we see what was enhanced geothermal, there's issues that you have to pay attention to. Fracking, you have to look at this, CO2 subsurface injections. We all have to worry about this. And what are we going to do about the volume expansion? These serpentinization reactions lead to about a 40% increase in the density. If you go from olivine to serpentine, it's about a 40% increase in volume. What's going to happen? How much of the world are we going to lift up? So metrics in a true white space. You know, this is one of those ones at RPE, we always have to put metrics on things. And when you're in a white space and you have no reference point, what do you do? You know, because everybody likes to say we're going to see X% improvement, X% reduction within this. And this is a challenge for us because nobody is looking at geologic hydrogen. You know, are we going to reference seeps in the ground? So I'm going to come back and talk about this eternal flame in Turkey and say it's putting out, you know, 250 cubic meters of hydrogen a day. We're going to go from there. We don't know about flux. You know, how much do we need to really get going to make this economical? And how do I measure improvements if we have no reference for this? Purity. This is a big discussion we're having is, you know, how pure do we want to get it to come out of the ground? I mean, natural gas you can set up such that after you bubble off all the CO2, you can get fairly high purity methane directly out of the ground and dump it into a pipeline. Is that going to happen with hydrogen? I don't know. So this is your guys' chance to tell me, what are the metrics for success? So if we're to come in and say, if I'm going to do midway checks, you know, let's say I fund out people into this area. You know, I fund people to do research. What are the midway? What am I going to be able to tell in that first or second year that they're being successful? Kinetic enhancement, equilibrium control, conversion of the available iron to, are these important? You know, environmental assessments. Are we going to be having water coming up out of the systems like we do with oil? What do the seismic air and the LCA look like for these things? I mean, these are questions that I'm looking for input on. And for a final, what do we look at? Cost at the wellhead. You know, what should the cost of hydrogen be at the wellhead? What about purity? Should it be greater than 20%? I picked 20% for a specific reason, is if it's coming up with CO2, wet CO2 and hydrogen, it happens to be the back end of an SMR, so you can do a pressure swing reaction. So I know what that costs. If it's not wet CO2, there's membranes that at 20% are economical for separating hydrogen from that. Greenhouse gas footprint. I mean, again, these are all swags, by the way. I just made these numbers up the other day. Potential deposits. I look at this and say, you know, we want a deposit that has a potential of greater than 10 million tons to be useful. That's a pretty big deposit, but it's also under the idea that allows you to do things, you know, like looking at potential productions. Can we look at making 1 million cubic meters from a field, not a well, from a field of 1 million cubic meters of 90 tons a day? Anybody know why I picked those last two? If it came down to, if you're looking at 33,000 tons per year out of a potential 10 million, that means you're reacting a fraction of a % of the available iron. So hopefully that's, I've been told by somebody, that will allow for geologic relaxation, so you don't get it. And by the way, I've told people that we can't look at this like chemists, because you're or a graduate student. Graduate students like, I want to have it happen. Oh, okay. If I wanted to do like a graduate student and have 100% yield in 8 hours, you look at them and go, what are you going to do with 10 million tons of hydrogen at once? We don't want that. So the question is, this is a manageable size. And somebody, again, we looked at the percentages and say will allow for geologic relaxation, and 1 million cubic meters per day is something you can develop a steel mill around 1 million cubic meters per day. So that, by the way, is what a steel mill requires to shift over to direct reduction of hydrogen. So really what I'm trying to do is develop this, and I'm coming up with the idea that we can do this for 50 cents to $1 per kilogram. You know, if you look at this, if you can stimulate this reaction, that is a game changer. Excuse me? Coming out of the ground. Same, so it's not a 700 bar. Just like the electrolyzer people are counting the cost of the hydrogen bubbling out of the water, not at 350 bar or 700 bar. That's another $1.50 per kilo it's going to cost you to compress it. So, what's your input?